All right, so today we're going to take a look at 5.6, which is inverse trig functions, and we're going to look at the differentiation for them. 5.7 is sort of the antiderivatives, but it's not exactly the antiderivatives of the inverse trig functions. You'll see when we get there, but it's, again, another antiderivative section. But this one's derivatives. Remind you of some things from trig, although you all took trig with me, many of you anyway, so you know this stuff, but just in case you have forgotten, okay? So an inverse trig function has a couple of names. We can either call it like inverse sine, or more commonly you'll hear it called arc sine. A third option is that sometimes you see it called, and this is what your calculator does, it puts the sign, it puts the little -1 up there. And remember that that does not mean the same thing as reciprocal of sine. That little -1 often means reciprocal when we're talking about things, because a multiplicative reciprocal is, a multiplicative inverse is a reciprocal, like for fractions, like 1/3 and 3, right? But arc trig functions, their reciprocal is not their inverse, okay? So we have the arc trig functions, which are, so taking a look first at sine. So sine has this property, and do you remember when we did sine back in trig, the sine function had a flowing pattern, right? It looked like a wave, right? And the pattern had the feature that you could put any value into it and you could get a sine value, right? You can take the sine value of any angle you want. And so the input into a sine function or input into any function is called the domain, right? So the domain on the original function, and we did this when we did inverses, is the range on the inverse function. So over here where you see range, well, let me write this down first and then I'll modify what I'm saying. The range, typically speaking, for a sine function would have been, the domain for a sine function would have been all real numbers. So we would see the range here. Now let me go back to domain because that's the one that's not going to change. Now the domain for arc sine would be the range for sine. Range is the y values. So when you're dealing with a sine function that looks like this, right, what y values do you see happening? Right, I'm going to switch around the order of what you said, Kendra, but that's right. So the smallest y value on this graph would be -1, and the biggest y value on this graph would be +1, right? So my domain for arc sine is that very thing, the range from sine. Now here's where the problem comes into play, and this is why I drew the picture. Remember when we did inverse functions back in 5.3, we said something about the fact that functions only have an inverse when? What was the sort of caveat, the condition? It's when they're 1-to-1. And if you take a look at the picture that I just drew, it is most definitely not 1-to-1, right? I draw a horizontal line, take the x-axis for example, it crosses the graph infinitely many times. Well, how am I going to get an inverse if I don't have something that's 1-to-1? Well, the way that I get an inverse is that I restrict the portion of the graph that I look at. So let me continue this picture down here. What we're going to do is we're going to cut part of the graph off. My picture isn't very symmetric, but if you look between the two pink lines, that piece of the graph is 1-to-1, right? So that portion, and you may not remember what values that was, but that portion of the graph is the part that we're going to define the arc sine on. And so the sine value on this picture would start from an x value of -π/2 and go to a y value of π/2. So we can't use the all real numbers. And the reason we can't is because then the function's not 1-to-1. But if we restrict our domain on sine, which means we're restricting the range on arc sine, then we have a 1-to-1 function and we can work with it just fine. Okay, so that's why we've sort of just chosen a portion of the graph. Now, let's do cosine the same way, and this time we'll start with the domain. So the domain for cosine is the domain for arc cosine is the range for cosine. So the cosine graph, we'll go back and do the quadrants when we're done. The cosine graph looks like this. Right? What are my range values, my y values on that graph? Yeah, negative 1 to 1, right? Same as sine, no differences. So those range values are my domain values for the inverse. So from negative 1 to 1. And we've got the same problem that we had for sine, don't we? This graph is not 1 to 1. So we have to sort of break apart just a portion of it that will be. And the way that we break apart that portion is we start at the y-axis, and we go over to the minimum value on the graph. And then between those two pink lines is in fact 1 to 1, right? So the value that we started at is x equal what? 0. Do you know where it ends, what x value that last pink line is at? It's at pi. So my range for my arc cosine, which was the domain for cosine, will start at 0, and it will end in pi. Tangent graphs are a little bit more interesting because we don't have to make the decisions for the sort of breaking points. They're obvious. So let me draw this graph. The tangent graph looks something like this. And then it does it again over here, and it keeps going, right? Everybody remember that one? So it's really easy to sort of see where the natural breaking point is to keep this 1 to 1, right? It's bounded by asymptotes, actually. And taking a look at that bounding right here, well, you know what? Let's do the domain first. The domain on the arc tangent will be the range for tangent. So what is the range for this graph? What are the y values you see? Right. So negative infinity to infinity, or you can write it as that r with a capital sign, or capital double R. Well, I'll write it both ways. Okay, so Dylan said negative infinity to infinity, or you can write it as all real numbers like this. You can put in any input into the domain for arc tangent. Now the range comes from the domain of the tangent function. So what domain values? Well, I need to be trapped between these two asymptotes. Do you know what those asymptotes were? They weren't the pi over 4s. They're actually the pi over 2s, the same as sine has. So, but they are even on each side. That feature is going to happen for us. This is negative pi over 2 to pi over 2. I promise we're going to do quadrant, but before we do quadrant, let me finish the domain and range for all of our inverse trig functions. So I'm going to switch to the next slide. So we've got arc cotangent, and arc cotangent had the graph that looked like, much like tangent, right? Whoops, let's make that dotted. Except that it was a decreasing graph, and the asymptotes are in a different location. So if I'm looking for the domain of the arc cotangent, that would be the range of this graph. What is the range of the graph you were looking at? What y values are there? Yeah, all real numbers, yeah? So I'll do the negative infinity to infinity that you told me earlier, though, Dylan. Okay, or you can do the all real numbers. What is the range? Well, if I want to do range, I want to look at the domain for that graph that I've drawn. And I need to restrict my view. And I can restrict my view just like I did with cosine, or just like I did with tangent. And the nice sort of restriction is right here, the most natural restriction. So what value am I starting at? What x-intercept, if you will, what x value, we'll say x value, does that first pink line hit at? 0. And because this is the graph of arc cotangent, and it's got the asymptotes, I can't actually equal 0. There's an asymptote there, right? So I'm not going to use a bracket. I'm going to use a parenthesis there, right? I use brackets over here because I could actually equal those end values. I made the mistake, and I did it. I noticed it when I did it here, and I didn't there. Let's fix this. Those also should have been parentheses because I can't equal those values because those are asymptotes on those edges. So we'll get that fixed. Where does the y or the x value end? What is that other second pink line x value? Close. Pi. So it's 1 pi actually. Trig functions always seem to occur at pi values. Those are the clean ones anyway, the standard trig functions. All right. Secant. Now, secant and cotangent, or sorry, secant, arcsecant and arccosine, I can't talk right, arcsecant and arccosecant come from sort of the reciprocal ideas, right? So if you'll remember these graphs were sort of odd looking, and when we learned how to graph them, what we did is we drew the sine graph, and then we used it to draw we used it to draw the cosecant graph. And when we did the secant, we used the cosine graph to draw it. So we kind of drew what we called a guide curve. And so when you're taking a look at secant looks something like this. It has sort of branches that go up and down. And they repeat themselves, of course, but this is the portion, of the natural portion of those branches. And as you can see, that's sort of unhelpful because both of those pieces, if I were to go in between the asymptotes like I did for tangent and cotangent, both of those pieces are not one-to-one individually, are they? No, they're not. But I can restrict the picture again, like I did with cosine and sine, and if I do just between those pink lines, it is one-to-one again. Right? I'm not getting the whole period, right? But I didn't get the whole period for sine or cosine either. I just got half of it. So it sort of seems natural and likely that would sort of bleed over into their reciprocals. So if you're taking a look at this graph and you're wanting to know the domain of arcsecant, we would be looking at the range on this picture of the graph of secant. What range do you have? Negative infinity to infinity? You're missing something in that.
0 can or equal 0.
It can't equal 0. What else can't it equal?
It can equal pi.
No. The pi and pi over 2 and all those pi values, those come along the x-axis. We're looking at the y-axis right now. What y values can my graph not equal? Will my graph never equal?
Between negative something. I forget what they are.
It is between negative something and positive something. Any idea what negative and positive something they are?
Is
Yeah.
0 here?
Yeah. Here, let me show you. I'll draw it in green. Whoops, I said green. I told it green even. That wasn't it. Let's try again. It really wants to attach itself to that other line. Okay, that's the best I can do. If it really were done well. There shouldn't be any part of that darker color that I'm using between, right? I've got a gap there. And that gap's actually where that guide curve went when we were in trig. That guide curve was happening of the cosine graph between there. And that cosine graph actually went from negative 1 to 1, right? So that cosine curve is oscillating between where my green lines are, which means the secant curve is actually below the green line and above the green line, and they are at negative 1 and 1 because the cosine values, range values, were negative 1 to 1. So my domain right here, it looks kind of awkward, and it does start with negative infinity, like Hannah said, but it actually has this value that it stops at. It stops at 1, and then union, and I'm out of space, but you could write it not right next to it if you weren't. And it starts back, sorry, that should have said negative 1. Let me get the negative in there. That's a negative 1. And then it starts back up at 1, and it goes to infinity. So if you start at the bottom of the graph and you go up, you've got all the range values you want until you get to negative 1. And then you have a gap, because that's the gap where cosine would be. And then you pick up with range values again once you get to 1 and go on up from there. All right? So that's my domain for arcsecant, is in negative infinity to negative 1, union 1 to infinity. The range, okay, so the range is going to be whatever I see in the domain over here. So the domain occurs between the pink lines. So starting with the first pink line, what x value am I at? 0. And what's my last pink line? It is at pi. So it's a 0 to pi, just like cosine, right? So the secant and the cosine, they're reciprocals. They have the same feature. But there's one value in the middle that it can't equal. It's this asymptote, right? It's at pi over 2. So my range ends up looking much like the domain. It's sort of broken into pieces. My range starts at 0, and it goes to pi over 2, and it stops, and it actually has a parenthesis that it can't equal the pi over 2. It doesn't equal that because that's an asymptote there. And then I have a union, and I start back up at pi over 2 because there's not really a gap like there was from -1 to 1, right? It's actually the same value. It's just that one little spot that's excluded. And then I can go all the way to pi after that. And again, I promise we're going to go back and fill in those quadrants. We're almost there. Let's do arc cosecant. And if I do that, I've got a very similar picture to what I had over here for secant, for arc secant anyway. And it looked like, well, let's draw it a little bit smaller, some more space. It looks like this. Okay. What do you think the domain values are going to be?
This.
Yeah, the same as it was for arc secant, right? The domain's doing the same thing because that's the range of these values. I can go from -infinity at the bottom all the way up to wherever this is stopping, and it's stopping at 1, -1. And then I have a gap. That's sine. It's occurring inside of that gap. And then I pick back up on this piece over here, but the y value is 1, and it goes up to infinity. So I have the same domain value that I had on arc secant. So this is -infinity to -1, union 1 to infinity. The range is a little bit different because my pink lines are going to be drawn into different spots. So where are my pink lines going to be drawn? I'm going to draw a little bit more of this graph.
Over 4.
Yep, one of them is going to be drawn at pi over 4. Yeah, it goes back to negative. Yeah, they're not. Yeah, it goes back over here to -pi over 4. Not pi over 4, pi over 2. My fault. I'm sorry. Yeah, pi over 2. Sine and cosine have a period of 2 pi. So from here all the way to this first asymptote is going to be 2 pi, which means the asymptotes are occurring at whole pi values, and I'm cutting them in half. So I am going from -pi over 2 to pi over 2 almost. What gets excluded? 0, right? There's an asymptote at the y-axis, so I exclude that. So here's union, and then I go from 0 to pi over 2. That is not sort of
Is that one of those
looking
like square?
Hmm?
Oh, no, they're both asymptotes. Never mind.
Yes, they're both asymptotes. Oh, you mean on the
Yeah.
on the edges of it?
Yeah.
Those actually could be brackets. You're correct. I should put those as brackets. Whoops. Get the right symbol here. Yes, Cameron is correct. Those actually aren't asymptotes like they were with, in fact, I had the same problem up there on the other one, didn't I? The edges of them are not representing asymptotes. They're actually a value that we can equal. Good point. It's just the one in the middle that needs to be not included. Okay, let's go back and do quadrants. So the quadrant issue is going to be sort of referring you back to unit circle stuff. So if you are going from -pi over 2 to pi over 2, what quadrant or quadrants is that referring to?
1 and 2.
So here's quadrant 1. Here's quadrant 2.
1 and 4. Yeah.
2. Here's 3. And here's 4.
What?
Yep. So what quadrant is it? 1 and
1 and 4.
1 and 4. Yeah. So why is it 4?
Because you're going backwards from 1.
Yeah, that -pi over 2 means I go pi over 2 in the negative direction, and negative means going clockwise around the unit circle. So if you go clockwise the same amount, you would get down to pi over 2 on the negative y-axis. So you're in quadrants 1 or 4 if you're dealing with sine.
Where is it in
Hang on just a second. Okay, so it's in quadrants 1 and 4. What about 0 to pi? What quadrants are we in if we're going from 0 to pi?
1 and 2.
That one's 1 and 2. What quadrants are you in if you're from negative pi over 2 to pi over 2 again? 1 and 4. What quadrants if you were from, let's see, 0 to pi? 1 and 2. Now, aside from the fact that these sort of have this missing value in the middle, I'm basically going from 0 to pi here, right? I don't actually get to equal pi over 2, but from 0 to pi, what quadrants could I be in? 1 and 2. It's just say 1 or 2. Yeah, 1 or 2. And then what quadrants could I be in if I were going from negative pi over 2 to pi over 2? 1 and 4. I know, 3 gets left out of the mix everywhere. Nothing's in quadrant 3. So all of this that you've seen so far is things that you did in Trig, right? It is, whether you remember it or not, I promise. You did it in Trig. And so the first thing we're going to do is we're going to talk about doing some of those problems that look like that. So we're asked to evaluate by hand, and the first one is arc sine of 1/2. So depending on the angles and the values you're given, you may end up finding things that your calculator can handle, and you may end up finding things that it can't. So that's why the by hand comes into play, is because often it ends up being values that you can't handle by hand. Here's the other deal, and I've said it once before, but I want to make sure everybody's there and remembering, we're not working in degrees. Calculus is never done with degrees. It's always radians. So I'm dealing with the arc sine of 1/2, and by the same token, what that means, and I did it over here, I didn't make a big deal about it, but over here, arc sine of x or y equals the arc sine of x if the sine of y equals x. So the first thing that I always do when I see these problems is I change this from saying arc sine of 1/2, and you can call it y or x or whatever you like. I change this to actually say sine of y equals 1/2. It reminds me that what I'm looking for is I'm looking for the location on the unit circle and which quadrants could I be in. This is sine. What was that? 1 or 4, okay? I'm stuck in quadrants 1 or 4, but this value for sine is positive, which means I'm where? I'm in quadrant 1 because I've got a positive value. Okay, so I'm up here somewhere in quadrant 1, and I'm looking for the sine value to be 1/2. Well, on the unit circle, when you learned your unit circle, and I made you memorize it because I did, those of you who had me for trig anyway, you memorized your unit circle and you took a quiz on it and whatnot. You actually have locations over here that are common locations for trig values, right? The angle measures you may remember if you're thinking in degrees were 30, 45, and 60. Those were the angle measures. If you're thinking in radians, they were pi over 6 for the first one, pi over 4 for the second one, and pi over 3 for the third one. Is everybody with me? I'm pretty sure there's a unit circle in your textbook if you don't remember them to refer to as well, okay? So you've got this unit circle thing going on. And we want to know where on that unit circle do we have an ordered pair, right? Because each one of those dots also corresponds to an ordered pair, an x and a y. And is the sine value the x value or the y value? It is y. And one of the ways that I had a student one time tell me that she remembered it was that it was alphabetical. So x and then y, right? X comes before y in the alphabet, and cosine, the C for cosine, comes before the S and sine in the alphabet. So the x and the cosine come first in the alphabet, and the y and the sine come second in the alphabet. So the sine value is the y value. So if you're looking for the ordered pair to have a y value of 1/2. Do you remember which one of those has a y value of 1/2? It's not 45. That is correct. Because at 45, what are those two values? They're square root 2 over 2's. So it's not 45.
Isn't it the first? No.
It is, yeah, it's actually pi over 6. It's this one right here, the very first one. This has the 1/2 here. If we had cosine in this problem, though, then that would be the pi over 3 value, right? So the answer here is pi over 6. Because what we're looking for is the angle measure that makes this happen. That's what arc functions do, is they're the angle measure that makes this sine value happen. So we get pi over 6 for this one. We're going to look at another one. Very similar, but on this one, I want to bring this one up in particular because your calculator is even less helpful on this particular problem, right? because you don't have a secant button, and because you have to think to yourself, how does this work to change it from secant into cosine when I've got arcs going on? Because it's not just straightforward like changing secant into cosine when there isn't an inverse function going on. So let's take a look at this one. The first thing I want to do is I want to rewrite it very much like I did the last one. I want to give the angle measure a name. I'll call it theta this time just because it sounds like fun. And so we're going to use theta. And I'm going to rewrite this then as the secant of theta equals negative square root 2. Just so that we're all on the same page, secant gets to use which quadrants, 1 and 2 or 1 and 4? 1 and 2. Secant is just like cosine, and cosine's in 1 and 2. So we're in either quadrant 1 or quadrant 2. Which one are we actually going to be in? 2. How come? Because it's negative. Anytime it's positive, you're in quadrant 1, right? Anytime it's negative, you're in either 2 or 4, depending on which trig function you're looking in. So we are in quadrant 2. And that helps us, right? Because that helps us remember which part of the unit circle I'm supposed to be finding angle measures from. If I'm in quadrant 1, my answers are always going to be either pi over 3, pi over 4, pi over 6. If I'm in quadrant 2, my answers are either going to be 2 pi over 3, 3 pi over 4, or 5 pi over 6, because those are the 3 measures in that particular quadrant. Now, here's something else let me bring up to you. If I'm in quadrant 4, if you go around the circle in the positive direction, you're going to be at 5 pi over 3, 7 pi over 4, and 11 pi over 6. But we're not going that direction. Remember, the trig functions go negative to get us into that quadrant. So I'm actually at negative pi over 3, negative pi over 6, negative pi over 4, negative pi over 3. So I actually go backwards into quadrant 4 when I'm working in that quadrant. I haven't seen one like that yet. You haven't seen one like that we've done. But all right, so this secant value, secant of theta equals negative 1/2. Again, I don't really think in terms of secant very well. Maybe you guys do. But I think in terms of sine and cosine really well with unit circles, because sine and cosine are the x or the y value. And I would like to be able to change secant into its reciprocal, because what's the reciprocal of secant? Cosine. So if I change secant into cosine, I did a reciprocal, which means I would also do a reciprocal on the other side of the equation. Well, the reciprocal of negative square root of 2 is, oops, I wrote it wrong, is 1 over negative square root of 2. Agreed? I did the reciprocal on the left, secant became cosine. I did the reciprocal on the right, which I did a 1 over. But again, I don't actually have 1 over square root of 2 specifically written like that on my unit circle. But what can I do so that it starts to look more like my unit circle? Over square root of 2. Yeah. So I can, we call that rationalizing, right, Cameron? Remember what I call rationalizing the denominator? Yeah. And that actually looks like a value that Dylan mentioned just a minute ago, doesn't it, Dylan? Yeah. And anytime we deal with that value, oops, I'm not supposed to say secant. We're in cosine now. Anytime we deal with that value, we're talking about the 45-degree angles, right? We have to decide which quadrant we're in and which one it is. So I already decided I'm in quadrant 2. So what, that doesn't look very good. What angle is this over here that I'm at? Right, 3 pi over 4. You guys had no idea how important trig was, did you? I know. What's better is that I know you should know it because you took it recently, as in a year ago. I don't know about you, Cameron. I don't know about Nidra, when the last time you guys were in trig, but everybody else gets no excuses. All right, let's take one more.
Well, junior year, but senior year, my calc teacher drilled us on trig the first 2 weeks.
Good. I'm glad to hear that.
But that's 3 years ago.
What's different about this one?
You have it inside of the sign.
Yeah.
So what are the arctangent 3 over 4 is on this sign?
Right. So if I erased the sign part on the outside, it'd look a lot like what I was doing with the other ones, correct? Yeah. But the problem is going to be with that 3/4. It's not going to necessarily be one of the nice, clean 30, 60, 90 type angles that we've been working in. So let me show you how you tackle a problem that looks like this. That is, it's got a arc function inside of another function. And again, we did this in trig. It's sort of a trick, if you will. And the trick is that you create triangles. I like triangles. Triangles in trig is probably my favorite part of trig. Because you guys learned triangles back in geometry, so It's not something that's sort of a foreign concept. You've seen it before. So create yourself a right triangle. I'm actually creating it as though I'm in quadrant 1 because I am. How do I know I'm in quadrant 1? Because I have a positive value, okay? My positive value, I'm in quadrant 1. So here's my angle here in the middle. I'm going to call it theta. So the theta is this arctangent value. Just like on the last screen, right? I let the arcsecant equal theta. Okay, the arcsecant of the angle of the value equals the theta angle. So I'm doing the same thing. I'm calling this theta. Now, with triangles, how is the tangent function related to the triangle relationship between sides?
The x value and the y.
You're close.
Or the opposite over adjacent.
Opposite over adjacent. And opposite to this angle theta is actually going to be the y value, actually, in my picture. But it's the opposite side. So the opposite side is the 3, because the arctangent is 3/4, right? Or I'm sorry, the arctangent of 3/4. So I've got the 3 on the opposite side, and Dylan told me it was over the adjacent, which is correct. This is my adjacent side, 5 down here. So this is 3 over 4. I said 5 because I'm almost getting to a 5, right? Where's 5? It's on the hypotenuse. How do I know the hypotenuse is 5? 3, 4, 5 is a common triangle you may know. What if it weren't a value that you were familiar with? What if I gave you 2 and 4? Yeah, you would do a Pythagorean theorem, right? So you could find the third side with the Pythagorean theorem. So we've created the triangle using the relationship of tangent to the sides of the triangle, which is opposite and adjacent, and using the Pythagorean theorem. It's sort of hidden in what we did on this one because it's a familiar one, but there is a Pythagorean theorem going on here, right? Okay, and I didn't do it, but that's the right angle down there at the bottom. All right, so what I do next is I look at this triangle, and I want to find, because I created the triangle based on the arctangent 3/4 part. Now I look at the triangle, which has this angle theta, and I remember what I know about sine, and I find the sine of theta in this triangle. And what is the sine of theta in this triangle? 3 over 5. Because you told me that tangent was opposite over adjacent. What is sine? Opposite over hypotenuse. The opposite side's 3, and the hypotenuse is 5. So the sine value is 3/5. Ready to take it one more step? No, you don't. Okay, this one actually is very similar. The difference is that it's not going to be the 3, 4, 5 nice pretty triangle, so we're going to have to work a little bit harder for it, but not much. So we've got an arc trig function inside of the trig function, which means we're going to be drawing a triangle, okay? So I draw my triangle, and it's a right triangle, of course. It says arc sine is -1, it's -5/6, excuse me. So where will the -5 go? Where will the 6 go? Oh, I shouldn't have drawn that picture already. I need to stop. I need to decide what quadrant I'm in. You tell me, what quadrant should I be in? Two or 4? It'll be 4. Why 4, not 2? Because it's, well, not because it's negative, because it's sine. Sine is in 1 and 4. Yeah, if we'd been in cosine, we would have been in 1 and 2. So I need to draw my triangle like this. So I need to slow myself down a little bit and draw my triangle in the right spot. Okay, so my angle theta is right here in the middle. Okay? And I need to take this theta angle, and I need to take the fact that arc sine of -5/6 is the information I'm given. And where will the -5 and where will the 6 go? Right. And 6 is the hypotenuse. Good job, Erin. All right, and I'm missing the third side, and unfortunately I'm going to actually have to find it this time. I don't just sort of remember it. So let's call it b. So this is b squared plus what?
25.
Yep, I'm going to write it as -5 for the moment squared, but yep, it's 25, and it equals 6 squared. So b squared, which terribly looks like my 6, I'm sorry.
I thought you wrote B squared.
I didn't, but that's a 6. Okay, and then I've got 25 on the left, and I have 36 on the right. That's a better looking 6. So if I subtract, what does b squared equal? Yep, b squared is 11, which means what's b? Square root of 11. So that's good information to have. Because now I can find the tangent in this triangle. What is the tangent of theta?
-5, well, not rationalized, it's -5 over square root of 11.
That's right. And that's exactly what I was wanting for you to give me, Dylan. So -5 over square root of 11, which is, as he mentioned, not rationalized. But you don't get to leave it that way, and I know you know that too, right? So we're going to rationalize it next. So I get -5 radical 11 over 11. Any questions? Okay, we're going to do one more. It'll finish up the trig portion of this, and then the next time we start, we'll start in on the calculus portion, which is the derivatives, okay? What's different about this one? It's an x. There's no numbers involved, are there? But that's okay. You guys like x. I know you do. It's your friend. So we're going to do the same kind of thing. Now here's the deal. The nice thing about the fact that it's x is that I don't need to worry about my quadrant situation. I'm just going to draw the picture in quadrant 1. Okay? So that's kind of the nice part. So let's draw my quadrant, or draw my triangle in quadrant 1, which would look like this with the theta here. Now this portion right here is theta. So what this is actually saying is that the secant of theta equals x. How is secant related to the sides of the triangle? Okay, let me ask the question differently.
How is secant related to the size?
Yes, like the opposite, adjacent, and hypotenuse.
Could you change it to cosine?
You could think of it as cosine. Okay, so yeah, let's think about it that way. You could do that. I like that. That's good. Let's do that, Aaron. So let's write this as cosine theta, and then we can write this as 1 over x. That'll work for me. How is cosine related to the sides of the triangle then? Yeah, adjacent over hypotenuse. So the adjacent side would be the lower side on this particular triangle, so that's 1. And the hypotenuse would be the x, right? Now I know there's an x in the problem, but could I find my third side in terms of x?
Yeah.
Yes. So I'm going to call it b again. You can call it whatever you want. Don't call it x, but something else. And I've got 1 squared plus b squared equals x squared. Everybody with me so far? Okay, good. I need to solve this for b. Well, this is 1 plus b squared equals x squared, because 1 squared is 1. So b squared is what?
Square root of x.
Square root of x
You guys already told me what b is, which is
plus
fine.
1.
Okay, so b is the square root of x squared minus 1. Okay, so that's what's on this side of my triangle. Square root of x squared minus 1. Now I need the sine of this triangle. And sine, as related to the sides of the triangle, is what? Opposite over hypotenuse. So the sine of theta here is opposite, which is square root of x squared minus 1 over hypotenuse, which is x. So your solution, which you could not have used the calculator for in any way, shape, or form, is square root of x squared minus 1 over x. Okay? Let me make one comment before I shut us down here quick. If you end up with a square root on the denominator for this one, like let's say we weren't finding sine, we were finding cosecant here. If we were finding cosecant, this would have started out, it would have been flipped, right? Because cosecant and sine are reciprocals. So I would have ended up getting x over the square root of x squared minus 1. You do not have to rationalize that denominator because you don't know what x is. There are some values for which that would already be rational because you don't know what x is. So if there's a variable underneath a square root in a denominator, you can leave the square root in the denominator. Okay? Make sense? All right.